só te quero encontrar, menina bela, porque você não quer amar, menina bela, eu mesmo só te quero encontrar.
Okay, so from all of your video information, you should have figured out that today's lesson is about quadratic functions and parabolas. How are they connected? Okay, quadratic functions, it says here, is going to model nonlinear data. Okay? So that's going to tell us that our graphs won't be lines for these types of equations. Okay, so let's kind of reflect here on our little frog jumping and everything. All right, we want in this game called Hungry Frogs, the idea is to get your frog positioned in such a way that he's going to intersect the path of the fly. Now, if that was linear, right? If when you shot something out of a cannon, it went linear, right? We'd have no problem, right? He's going to go straight over there. But because it's a parabola, it's a little more. Okay, so when you have the idea of a parabola, it's an arcing. Okay, so you can see here the frog comes up, and then what's going to happen next? How will the frog, will he just drop? Okay, well, let's take a look and see. If he completes it, yeah, it comes down the same way he went up. Okay, you get this idea of symmetry. Okay, so he comes up and comes down the same path. All right. Okay, so since we have this, since we have a graph of the path, the red points here represent data sets that we could possibly collect along the way. If we had an actual frog, right, we could measure, distance away from us or from the cannon and distance from the ground, and that's what they've plotted along here. So if we have data in a graph, we can put it into a table. We want to estimate our various points along the way. Okay, so right here, this first point appears to be 0, 0. So we're going to write in our table 0, and then 0. 0, 0. Okay, that's our starting point. And then here we came over 2 feet and went up not quite to 2. We're going to estimate that as 1.8. So 2 and 1.8. And then the next point at 4, we're going up a little more than 3, so we're going to call that 3.2. Okay. And then the next point we have is over here at 6. Okay. And it looks like it's at about 4.2. And then the next point would be at 8 and 4.8. Looks like we're slowing down a little bit here, right? The initial, he went a lot farther each foot. Okay. All right, and then at 10, we appear right dead even with 5. So, and that's the top of our arc there, our parabola. And then he starts coming back down. So 12 is at about 4.8. 14 is at about 4.2. 16 at 3.2. 18 at 1.8, and 20 is back down on the ground at 0. Okay, so you'll notice each of my y values has a double, right? Except for the 5. The 5 didn't have a double. It's right up here at the top, right? So that was my maximum. My maximum doesn't have a double. Okay. So all right, so let's notice mark some things on here about that are of important. We've talked before. What are some things that are important? X-intercepts, right? So right here is an x-intercept, and here is an x-intercept. Okay, and those points are 0, 0, and 20, 0. This point is also my y-intercept, so my x and y intercepts are one set at least is 0, 0. Okay. My maximum point here, right? This is my maximum, is at 10, 5. And those are going to be some of the main points you want to look at when you're talking about a parabola, because where does it intersect the x-axis and what's its maximum? Because if we know that, right, we can see, because of this idea of symmetry, if I know where I'm beginning and ending on the x-axis, then where my maximum is, then everything I can plot what's going on this side, and it's going to mirror on the other side. Okay, so this is called my axis of symmetry. Because on that line, right, everything reflects. Okay. Now, based on the numbers we have here, it's pretty telling. You're not going to be able to draw a straight line right through most of the points. Even if you tried to do a line of best fit, where would you go? Over here? Well, it doesn't really tell the story at all, does it? Okay. So this is nonlinear data, and so a quadratic function is what we're going to have to use here. So you may remember from our first video what this path is called, what this shape is. Okay, well, it's called a parabola. Okay, and all quadratic functions graph to be parabolas. So parabola is the shape of a quadratic function. Okay. Okay, So since we can describe the path of the frog using the quadratic function, okay, and a quadratic function, you might want to write this down, is a nonlinear function that can be written in this general form. Okay, general form, this is also referred to as standard form. Okay, so general form or standard form. Y equals ax squared plus bx plus c. And that should look pretty familiar to most of you because that's what we've been factoring for the last 2 weeks. Okay? All right. Notice there it says a cannot equal 0, because if a equaled 0, right, then this term wouldn't be there and it would just be our linear function. Okay. All right, and the graph of a quadratic function is called a parabola. What we can see here is this U shape, right? It's what we call a smooth curve. Okay, and this is where some of us have had discussions earlier in the year when you would say a straight line, and I said by definition a line is straight. Okay, some of you would say, well, this is a straight curve, right? But what mathematicians refer to this as a smooth curve. Okay, so we have a smooth curve, and that makes this symmetrical U shape, and that's a parabola. Okay, so the graph of a quadratic function is curved, and the graph of a linear function is a straight line. Okay, and since it's a function, we can talk about its domain and range. The domain of a quadratic is, well, this particular quadratic that we're showing, it starts at 0, right, and then it appears to go on forever. Okay, because of our situation with the frog, we're not going to have anything over here, and when it hits the ground, that arrow is kind of misleading, isn't it? Because when he hits the ground, is he going to go into the ground? Suppose maybe if he hits water instead of ground, he could possibly go down. But generally speaking, you know, the frog's going to leap, catch the fly, and stop. So, so usually if it's just a quadratic and it's not attached to a situation, we say the domain is all real numbers. Okay? Now the range is a little bit different this time because you see how this one's going to stop? Right? We're not going to go any higher than 5. Okay? Even if we have arrows here and it's going down forever and ever, the domain is going to have a limit. Okay? And that's going to be either a maximum point or a minimum if the parabola turns the other way. Okay, so the range is never going to be all real numbers for a parabola. Okay, so here's just a quick comparison between the two. You can see a linear function, which was y equals mx plus b, and a quadratic function, which is y equals ax squared plus bx plus c. All right, so a quick game of quadratic function or not a quadratic function. All right, so this would be a lot more fun if we were doing it together, but unfortunately I'm in Austin, so you're going to just kind of have to bear with and watch me play. Okay, so this first one, it doesn't have any squares, right? And if I combine my like terms there, 4x plus 2x, it's still going to be just 6x. So I'm going to say not a quadratic function. Okay. Y equals 82. Hopefully you remember something like that. That's just going to be a horizontal line. Okay. I think the picture here is pretty clear. That's a line, so still not a quadratic. Okay. Here we have a squared, but it's not on the x. So I'm going to say that's not a quadratic. Okay. This has a curved shape to it, but then it goes off and does something else, so not a quadratic. Right. But this is that nice curved U kind of shape. It's pretty flat, but still I think that one's going to be a quadratic. This one's a very pretty quadratic, so I'm going to put that right on up there. Okay. This one has a squared, right, but it's got 1 over, and that just, I don't think we would be dividing by x squared in a quadratic. So I'm going to put that one over here. This one very nicely, x squared. It's not in standard form because the y is still on and the x are on the same side, but I think that one's going to be a quadratic. Okay. This one doesn't have a squared written, but if I were to multiply 5x times x, I'm going to get 5x squared. So that one for sure. That one's got the x squared, and that one's got an x squared in it. So I think so. Let's check it. Yay! Okay, so what you want to do right now is sketch these onto your page so that you have representations of what is a quadratic function and what is most assuredly not a quadratic function. You might want to pause the video here to give everybody time. Okay, so moving on. Okay, so what are the characteristics of a quadratic function? Find the x and y intercepts of each parabola. Okay, so these are some things that it's going to be important for us to identify when we're talking about our parabolas. Okay. Okay, so an x-intercept is where it crosses the x-axis. So we can see here the red parabola is crossing at that point. So we would simply call that -4, 0. Y-intercepts, right? Well, it seems right there is the only place that's crossing the y, and that's at 0, 8. Okay. Now our blue parabola is crossing the x-axis twice, so we're going to recognize both of those points. And since we're counting by 2's, this would be at 1, 0. And then the other point is at 5, 0. Okay, and where is it crossing the y-axis? Down here at -5. So that point is 0, -5. Okay. So now we want to write the equation of the axis of symmetry for each parabola. Okay, so before we do that, let's define axis of symmetry. So you want to write this down on your paper. The axis of symmetry is the vertical line that divides a parabola into 2 congruent halves, right? So it divides it in half. There's the same on each side. Okay, if you need to, pause the video so you can get that written down. All right, so now that we know that what the axis of symmetry is, right, how do we find its equation? Okay, well, it's pretty easy from the graph because it's going to go through the vertex right here. Okay, that's what that point is called. The maximum and minimum point is called the vertex. So we're going to go through that, and it's halfway in between the two sides, right? So like we can see here we have a point, and here we have a point. So this distance is 2. And this distance is 2. Okay? All right, so it's a vertical line, so it's going to be an x equals line, always. And what does x equal? Well, it's going through the axis at -4, so x equals -4. Okay? For our blue parabola, again, we can see it's going through the vertex, the maximum point, right? It's halfway between 1 and 5. Okay? So that's going to be located here at 3. Okay, so x equals 3. Not too hard to find the axis of symmetry from the graph. Okay, so now let's take a look at what our vertex, where our vertex is located. Okay, and we already said the axis of symmetry was going through our vertex. Okay, so this one's located at -4, 0, which just happens to also be our x-intercept. But that doesn't always happen, as we're going to see in just a minute. So -4, 0 is the vertex here, and then over here on our blue one, we came over 3 and up to 4. So that one's going to be 3, 4. Okay. Okay. And let's go ahead and get a definition of vertex while we're here. This you should jot down on your paper. Okay, the vertex of a parabola is the point at which the axis of symmetry intersects the parabola. Okay. All right, and so the maximum or minimum. Okay, this is the very lowest point, then it goes on forever. So this graph, we would say, has a minimum. Okay. And here's our definition. The minimum is the y-coordinate of the vertex when a parabola opens up. Okay. All right. The maximum is the y-coordinate of the vertex when a parabola opens down. Move that out of the way. So the maximum is the y-coordinate of the vertex when a parabola opens down. So let's see what that means for us. Is it a maximum or a minimum here? It's a minimum. It's the lowest point. And it is located at 0 because it says it's the y coordinate, right? Okay, and then this is opening down. So this would be a maximum point right here, and that is 4. All right, so now we want to look at all the pieces that we've just talked about. Let's see how well we remember. Okay, so kind of quiz yourself before it shows up on the screen. The x-intercept. An x-intercept. Where would an x-intercept be located? Okay, that's right. We have an x-intercept right here because that's pointing to where it's crossing the x-axis. All right, what about a y-intercept? Okay, well, here's my y-axis. So right there is pointing to that one. So that's going to be my y-intercept. Okay. All right, let's see. Vertex. Vertex is located on the axis of symmetry. So that's where it's intersecting. So there's my vertex. The axis of symmetry itself is my line. So that's going to be the axis of symmetry. And then this is the bottom of the graph. All my numbers are getting bigger from here, so this is a minimum point. Okay. All right. So we want to complete this table for y equals negative x squared plus 4x plus 4, then plot the points to sketch. Okay. So at this point, I hope you have your calculator handy because that's going to make it a lot easier for you to answer this kind of question, because what you want to do is substitute the x values they've given you into the equation. Okay, so go ahead and pause the video for a minute and fill in your table. Okay, so what you should have found out that negative 2 give you a value of negative 8. Negative 1 gives you a value of negative 1. 0 gives you a value of 4. 1 gives you a value of 7. 2 a value of 8. And 3 a value of 7. Then plotting the points. Negative 2 would be represented here. Negative 8 right there. Negative 1 be about halfway, and then halfway, so just kind of hanging there. 0, 4, 1, 7, so here's 1, and then up to 7, then 2, 8, and then we come back down 3, 7. Okay, so that's what hopefully you got on your own. Where's my axis of symmetry going to be? I'll change colors here so it'll show up. Nice red, I think. Okay, so we're coming up, and then we started to go back down. So this is my maximum point, also going to be my vertex. So here is going to be my axis of symmetry. Okay. Sorry about the poor drawing. Hopefully yours will be straighter. And it's going to be located at x well, it's not going to be located at the formula or the equation of this axis of symmetry is x equals 2. Okay. All right. So what do you think is going to happen when the x is 4? Where are we going to be? Okay. All right. You've got that mirror image going on. So we're 1 away on this side of the x-axis. Right? So the next line we predict would be here. Okay. And then similarly when we go out to 5 and then 6. Right? So we're seeing these points are equal distance from our axis of symmetry. And they're the same distance from the x-axis. Okay, so how can you use symmetry to graph a quadratic function? Right. Well, we have this nice little formula here that says the axis of symmetry is going to be at the opposite of b over 2a, and when we have our formula here, right, we have the a and the b is in front of x squared and x, so we look in front of x squared and x, and we see that a is -1 and b is 4. So our axis of symmetry would be x equals the opposite of 4 over 2 times -1. And so that is x equals 2. And we look at our picture here, and they have drawn that in for us, and indeed it is at x equals 2. So how would that be helpful? Well, if we know where the axis of symmetry is, right, we know that the other points are going to be equal distance from each side. So if I know where for instance here, where it was crossing the y-axis, right, then I've got that point, and then I would have a point equal distance on the other side of the axis of symmetry. Or if I knew maybe where it's crossing the x-axis. Okay. The vertex would be helpful though, right? Because I know it's going to be on that line, but exactly where on the line, I don't know. Let's take one from the beginning. How can you use symmetry to graph a quadratic function? So if we graph this by first identifying the axis of symmetry, okay, so we want to take our formula, right, and we have x equals the opposite of b. B is -12 over 2 times a is 1. Okay. So when we multiply all that out, we get 6. So x equals 6. So right here, on this line right here, that's where my axis of symmetry is going to be. All right, so now that I know that, if I knew some points, I could graph those, and then I'd be able to figure out where the other points go. Okay, so let's see. What about 3? Right here is 3. Okay, so if I put 3 in, that'd be 3 squared minus 12 times 3 plus 33. Okay. So that, I'm probably going to grab my calculator and figure that out. And I came up with 6. So here I'm going to put 3 and 6, and then I'm going to graph that 3 and 6. There we go. Okay, what's another good point? How about 4? Let's check out 4. What happens when we put in 4? Okay, so I'm going to change this. And now we're going to have 4 squared minus 12 times 4 plus 33. And that is going to be 1. Okay. So I go 4 and then 1. All right. Now based on this, I'm thinking my curve's going to come around like this. So, all right, so my next thing, well, my axis of symmetry is here at 6. Maybe I should try 6? Or, no, I think I would get another point before that. I'll try 5, and then I'll try 6. Okay, so we're going to plug in 5 just the way we did 4, and should get -2. And then we plug 6 in, and we get -3. Okay, so 5, -2, about there, and 6 will be at -3, which is here. Okay, so now that we've worked our way into the axis of symmetry, we know we're going this way, right? Coming in, getting closer and closer, and making that nice curve. So we should come out the same way. So this point would be my next, which is, we're now at 7, right? But we're at -2. Okay, and then as we come up a little more, right, we're going to hit here. Okay, so that was 4, 1. So right here we'll be at 1. Okay, so we're coming up. So that's 8, 1. And then 9, we should be at 6 because we're coming off the other side. So 9 is about here and 6 is here. Okay. So we get that nice symmetry. So we only had to find a few points on the left side of the axis of symmetry, and then we were able to just count it out, reflect it for the remaining points. Okay, so we have the height h of a launched frog, right, from the beginning of our little activity here. And it can be modeled by this equation, and t stands for our time in seconds. So we want to write the vertex in our shaded row. So where's the vertex going to be located? Well, that may require us to do a little more work. Okay, so and then once we know where the vertex is, we can use symmetry to find the other values to complete the table. Okay, so the vertex, oh, the vertex had to be on the axis of symmetry, right? Okay, so since the vertex is on the axis of symmetry, if we find out where the axis of symmetry, or what the x value is at least, right, we can do that. So the opposite of b, which is 32, divided by 2 times a. Okay, so the opposite of 32 divided by 2 times -16, -16 is 32. So 32 divided by -32 would be -1, but then we take the opposite of that, so that means +1. So our vertex is going to be at 1. And it's x because that's our line, but because in the way our equation is written, x is represented by t. Okay, so 1 is going to be where that's located, and so h equals -16 times 1 squared plus 32 times 1. Okay, and we do that. 1 squared is 1, so that's going to be -16 plus 32, which is 16. Okay, so h would be 16 at that point. All right, so since we're at 1, let's back up a little bit. We're counting in seconds. Okay, so I think we probably need to put maybe 0 and 0.5 because that frog moved pretty fast. So we want to give ourselves a little bit of time there. So at 0, right, if we substitute 0 in for our t value, well, at 0, he's still on the ground, right? So our height was only at 0. Okay, so after half a second, what's that going to be? Okay, so h equals -16 times 0.5 squared plus 32 times 0.5. And that one I went to my calculator. I didn't want to do all that in my head, sorry. So I got that h would be 12. Okay, so based on that information, if we went to 1.5 seconds, we should also be at a height of 12. And if we go another half, which would be 2, we should be back at 0 because we have that reflective thing going on. Okay? So 0, 0. Gonna be right there. 0.5, let's see. Looks like we're counting by 0.2, 0.2, 0.4, so 0.5. And then we're going to be at 12. Right there. Okay, and then 1 would be here, 16. And then 1.5, there's 1.4, 1.5 would be here. And then 2 out here is back at 0. Okay. All right. So we've plotted our points. And there's our graph. Let me go ahead and clear my writing off of theirs. Okay, and you can see very clearly. All right, so what is our maximum height if we were trying to answer the question? Well, right here at 16, right? Okay, so let's bring that down to a reasonable size. So our maximum height is going to be at 16 feet, which is also our vertex. So you're going to graph now this function. Go ahead and pause the video and come up with your graph, and then we'll check. Okay, let's check it. How'd you do? Okay. All right. Let's reset. Now try this one. Go ahead and pause the video. Now we check. All right. Okay, how can you change y equals x squared to make other quadratic functions? All right, so y equals x squared is called the parent function. A parent function is the simplest function in a family. Okay, for the linear family, that was y equals x. For the quadratic family, that is going to be y equals x squared. Okay, so the parent function is y equals x squared, and this is the way the graph looks. Okay, and so every quadratic is just a transformation of that. Okay, and remember, transformations can be reflections. They can be stretches, translations. Okay, all right. So what effect does changing k and y equals x squared have on the graph? Okay, so k they're showing is being added to the x squared. So let's see what happens when we change k. What if we added 1? Okay, what happened? Not sure? All right, let's see what happens when we add 2. And then 3. All right, let's go backwards. What happens if we do negative 1? Hopefully your answer was that the change in k causes the parabola to shift up or down the y-axis. Okay. All right. So what happens if we add or subtract to our x value here? What's going to change then? All right. So let's see when we subtract 1. Okay. Subtract 2. Subtract 3, what happened? It moved over to the right that many units, right? Okay, so what do you predict is going to happen when we go to when we have a negative number, right? When we subtract a negative number. Oh, it's saying plus 1, so we're subtracting negative 1, so plus 1 is moving it to the left. Okay, so that's what happens when we change our h value. Okay. Let's see. What happens if we change the number in front of x squared? Okay, so this is when the number is at 1. That's our parent function. So what happens if we go to 2? Oh, it got much more narrow, right? And then 3, even more narrow. Okay, so it didn't move it. This time it caused it to change its shape. So it's kind of like a stretch or whatever. Okay, so let's see, if we go to 1/2, it got wider. So negative 1/2 is a lot less, so I think shouldn't it get even wider? Let's see. Oh, no, it didn't get any wider, it just flipped over. Huh, what happens with negative 1? Same thing. It's still the same exact size, it just flipped over. Now negative 2, it got skinnier, right? But it still flipped over. And negative 3, it got skinnier, but it's flipped over. Okay, so I think when we change the number in front of a, if it's positive, right, then it's going to open up. And if it's negative, it's going to open down. And the bigger the number, not the negative part, but the bigger the further away that number is from 0, the skinnier or narrower my graph is going to be. And the closer I am to 0, the wider my graph is going to be. Okay. All right, so let's compare some of these functions. Okay, so here's y equals x squared. And then here we're going to subtract 3 from x. What did we say was going to happen when we subtracted 3? Right, it should move to the right. So, and it did. Okay, so awesome. All right, now what happens if we add 2 to that? What should happen? It should go up. Let's see if that happened. Absolutely. Same shape, just moved up. Okay. Now, let me take this one off because we're going to do this. So what happens if I put a negative out front on this? Oh yeah, it should flip over, right? And it did. Okay, so that worked. And then this negative 5, let's see, that's a number. And it's in front of where the x value is. So that should get really narrow. All right, let me take this one off. So we're just talking about this one. And we're just changing that from negative 1 to negative 5. So it should just be the same thing but narrower. And it is. Awesome. Okay. All right, so now your job is to match each of these. Okay. So go ahead and pause the video and then you'll check. Okay. All right, so now that you're looking, we can tell that this is a negative out front, so it should be opening down. And the plus 3 means it should have moved to the left 3 and up 5. So let's see, opening down, yes, but it went to the right, so that's not it. Opening down, and it went to the left of the y-axis. Let's see, 1, 2, 3. I'm talking about the vertex moving here. Okay, so that went 3, and then it should be up 5. Let's see, 1, 2, 3, 4, 5. I think, there we go. Okay, so then we have this one is positive, so it should be opening up, and it just moved up 2. Let's see, so positive, but it's down 1, 2, 3, 4. This one went up 2. And this one did not go up at all, so it must be that one. Okay, and then here we have 3 out front, so it should be kind of skinny. It's positive, so it's opening up, and this minus 1 means it went to the right one. So this one's opening up, kind of skinny, and it's to the right one. Okay, x squared minus 4 just means it moved down 4. Let's see, 1, 2, 3, 4. So I'm going to try that one. Okay, and then let's see. This says it went up through, to the left one and up 3, and it's opening up. Well, my 2 remaining are opening down, so that one can't be any of the ones that I've got. Let's look at this one. This one's down 1, and that 4 means it should be kind of skinny. Down 1 and kind of skinny. I think we have an answer there. All right, and then here it's the only one left, but let's kind of check. It went to the right 3, 1, 2, 3, and then up 3, 1, 2, 3, and it's reflecting down, so cool. All right. Yay, we are correct. So make any changes you need to so that you have the right equations to show. All right. So the path of the frog is modeled by this equation now, so they've changed it up a little bit. Can the frog catch the flies? Okay. If I didn't want to go through that whole process again of finding the axis of symmetry and plotting points and then graphing over, I could use the idea of the transformations to create this graph, right? Because I could start off with the parent function, and then I could move it based on what's going on here. So like I could start off at my vertex being at 0, 0, and then move it to the right 6 here, and then up 9 should be here. Okay, let me get my pen back. So 6, 9. So that's where my vertex would now be, right? Okay. It's going to be compressed or made narrower, right, by this negative 1/4. So that actually means it's going to, sorry, it's not going to get narrower. It's going to be wider than my parent function would have been. Okay. So since I know it's going to be there, and I know he's starting here at 0, 0, I kind of have an idea that it's going to be something like that, right? And then since it's halfway from 0, 0, I can count that over. That's 6, so I should go another 6 out here, and this is when my frog should be hitting the ground. So I should be able to do something like that. Okay? It's not a perfect graph, it's a quick sketch. Not too bad, okay, but I think we'll take theirs because they make a much nicer sketch than I did. Okay, and then so that's the red frog's path. Let's take a look at, we have a blue frog, so we want to we're going to move our cannon over, right, because we want this blue frog to pick up as many of these flies as possible. Okay, so where should we move our cannon to, huh? Let's see. Ah, right there. Okay, and you can see each of my flies is now a data point. Okay. All right, so since we know the new maximum here, right, is at 14 and 6. Okay, the maximum's at 6, but x is 14. We can, and we knew our maximum here was at 6 and 9, right? And it appears that, you know, he didn't. Did he get any wider? I don't think he got any wider. I think the cannon does the same arc each time, right? Okay, so based on that information, I think we could change our equation, leave it at negative 1/4 because he's still, the flies are just as far apart, but we're going to change it to x minus 14 squared, and then we went, but we're no longer up 9, we're only up 6. Okay. There we go.